Hi, welcome back. In the next session, we're going to use these crucial concepts to create optimal sample size. So we're going to talk about sample size, which we've already talked about in the previous session, accuracy, which we've also talked about already, and then variability, which we actually already talked about in the class about stratified sampling. But I will repeat with some more examples in this session, and then confidence interval. So each of these concepts jointly helps to create the optimal sample size. So this session is a couple of rules. It basically is a couple different sample size axioms that are pretty theoretical, but I'm going to try to explain them with as many examples as possible. So just bear with me, and if needed, pause the video so you can listen to it again. So the first axiom is that the only perfectly accurate sample is a census. Think about that for a minute. You know what accuracy is, right? Because I already talked about it in the previous session. So accuracy is really how close are your results to the true population's findings. So any result you find in a sample, how close is that to the truth, to the actual population's findings, which you don't have because you never asked the whole population. Now, a situation of perfect 100% accuracy is not possible. You always have some sample error, except when you work with a census. Now, a census is a theoretical notion. A census doesn't actually happen. A census is theoretically the idea of every member of the population, so the whole population at large. Now, in that case, you don't need a sample frame because you take everyone in the population. The only reason why we have a sample frame is to use that as a basis for sampling. But with a census, we don't sample, we just take the whole population. So if there's no sample frame, there's no sample frame error, remember? And if there's no sample frame error, there's also no sample error. And if there's no sample error, that means we have maximum perfect accuracy. Now, this is only a theoretical idea. This is in reality just not feasible. In reality, we always have some sampling error because that's the consequence of sampling, remember? You always have sampling error because there's sampling and also because of the sample size. In the sense that if your sample is larger, you're going to have less sampling error. If your sample is smaller, you're going to have more sampling error. Now, besides sampling errors, there's also such a thing as non-sampling errors, which we will cover actually in a complete next online class. So that's a different topic. Non-sampling errors are all other errors. So anything related to data collection errors, question bias, wrong problem definitions, wrong analysis, and so on. So basically anything except sampling errors are called non-sampling errors. So we'll cover that next class. So for now, we focus on sampling error only. Sampling error is something that only occurs when we sample, of course. And when we don't sample, if we use a census, then you have a perfectly accurate sample or a perfectly accurate piece of data. This immediately goes hand in hand with the second axiom. And the second axiom says that a probability sample will always have some inaccuracy. It will always have some sample error. And that's true, right? We talked about how probability sampling methods give you more representativeness, but that's one thing. The sampling method determines representativeness. Now, every sample, even the really good probability samples which give you good representativeness, still give some inaccuracy. You'll always have some inaccuracy. Why? Well, simply because you sample. As soon as you sample, in order to sample, you need a sample frame. Sample frame comes with sample frame error. A sample basically is based on that sample frame, so as a consequence has some sample error. So no random sample's value is a perfectly accurate reflection of the population's value. So you'll always have some inaccuracy. The third axiom is that a larger probability sample will be more accurate than a smaller one. So the larger a probability sample is, the more accurate it will be. In other words, the less sample error it will be. And this goes hand in hand with the previous idea as well. I already talked about how enlarging your sample size will make it more accurate. Of course, if your sample is a probability sample to begin with. A probability sample is necessary. It's basically like a prerequisite to get representativeness. And in probability samples, you can start playing around with the sample size, with a larger sample size creating more accuracy. However, this relationship between sample size and accuracy is asymptotic. So that means that you have the law of diminishing returns here. So as you can see in the graph on the slide, on the horizontal axis, the x-axis, you see sample size and you see it goes up. Now on the y-axis, the vertical axis, you see sample error, which is an inverse of accuracy. So larger sample error means less accuracy. So what you see here in this graph is that with a smaller sample size, you have high sample error. So that means you have low accuracy. Now, as you move up on the horizontal axis, so as you increase your sample size gradually, your sample error is going to decrease. In other words, your accuracy is increasing. So your sample error is decreasing, which means you get a better and better, a more accurate sample as your sample size goes up. However, this graph will never reach zero, so your sample error will never hit zero. You see, for example, on the right side of the graph, that even if you have a sample of 2,000 people, your sample error will not even be that much lower than if you have, let's say, 1,700 people. So that's why I talk about this law of diminishing returns. You can keep increasing your sample size, but your sample error will keep going down, but will never reach zero. And why will it never reach zero? And that's because you're still sampling. It's still a sample, and a sample will always have some sample error, or will, in other words, will always have some inaccuracy. The only way to get perfect accuracy would be to do a census, which is not even a sample. It's the whole population, as we said in the first axiom. So this is something to keep in mind, that asymptotic relationship between sample size and accuracy. You can also see that same idea reflected in this graph here, or this table. It shows you how on the left side, if sample size, or n, small n, goes up, how sample error goes down. And sample error is expressed as a percentage, the percentage of sample error. So how much of your result is basically sample error. This is the inverse of accuracy. As you can see, sample size going up means sample error going down, but at some point it's just not worth it anymore. You can keep increasing your sample size and you're still gonna have some sample error, so at some point you're gonna have to make a trade-off. The fourth axiom is that sample error can actually be calculated with a very simple formula. And I show you the formula on the slide right here. I'm not going to ask you to replicate this formula verbatim, although I do need you to understand this formula perfectly, and as a consequence of understanding it, you're automatically going to be able to replicate it anyway. So I do need you to know this formula. I'm just not gonna ask you literally, but it would be a very good idea to memorize this formula anyway. So this is the formula for sample error, which is, like I said on the previous slide, is expressed as a percentage. So we have 1.96, which is a constant, and this constant corresponds to 95% confidence. You might remember from MIS why that's the case. It's basically a convention that researchers use 95% confidence in their results. That means they tolerate a certain amount of error still anyway, because you never have 100% confidence in your results. Then we have P times Q in the numerator and sample size, symbolized by small n, in the denominator. So P times Q stands for variability. That's the idea of variability. Variability can be expressed as a percentage, and in that case, P plus Q together would be 100%. So Q is always 100% minus P. I will give you some examples of variability on the next slides as well. So sample size is in the denominator of the equation. So this equation actually shows you that variability and sample size have an important impact on sample error. Variability is the amount of disagreement, or dissimilarity versus similarity, or also called variance, in respondents' answers to a specific question. High consensus within a group or within your sample means low variability. Low consensus within a group means high variability. In other words, it's a way to measure to what extent people are on the same page. And this could be about an opinion-related question, or could be something physically verifiable, such as shoe size or height or age. Let's take the example of age. High variability in age would be a group of people with very widely differing ages. So ages that are very wide apart. So maybe there's babies in the room and there's elderly people in the room. So age ranging very widely. That's high variability in age. Small variability or low variability in age would be, for example, my students in class in Marketing 470, they're usually more or less the same age. They're all somewhere between usually 20 and roughly 24, 25, most of them. Of course, there could be some outliers, but overall, you have a low variability, so a low dispersion, a low level of spread outness, if you will, of this variable, in this case, age. But this can also be the case with opinions. When you have the variable, for example, would you vote yes or no for legalizing marijuana federally or nationally, then you could have potentially everyone being in the same boat, so basically agreeing to legalize marijuana or to not legalize marijuana. And then high variability would be if people are completely disagreeing. So basically, if you'd have a split in a referendum where, let's say, 50% of people says, no, I do not want to see marijuana legalized, and the other 50% says, yes, I do want to legalize marijuana. So in that case, you have a very high variability because people are not on the same page. Now, variability is expressed by the letter P, small letter P. And like I said in the previous example, if people are very much on the same page as on the right side in this graph, then they agree, then there's little variability. So you might still have some people in the no camp, you have a majority or an overwhelming majority in the yes camp. So people tend to be on the same page. So this is, for example, a split of 90 versus 10. Now, if you have high variability, people don't agree on whatever question you ask them. So you'd have, for example, a 50-50 split or a 45-55 split. So in that case, you have much higher variability. Now, variability is in the numerator of that equation, right? Of the fraction that calculates sample error. So the largest possible variability you could ever have is 50-50. And you can calculate it if you don't believe me. P times Q, or 50 times 50 is 2500. So any other variation on P times Q, let's say 40 times 90 or 20 times 80, is always going to yield a lower variability if you were to calculate it. So why does this matter? Variability being in the numerator of the fraction means that if you have high variability, so if your numerator is large, you're going to need a larger sample size. So in the denominator of the fraction is sample size, you're going to need a larger sample size to compensate for that high variability if you still want to keep the outcome of your fraction small, if you still want to keep your sample error small. Because the 1.96 is just sitting there, that's a constant. So the only factors that you can really truly play with, unless if you would change the constant, of course, but the factors you can truly play with to some extent are variability in the numerator and sample size in the denominator. And like I said, if variability is high, then you could just keep the same sample size, but you're going to have a high sample error as a consequence. That's simple mathematics. If your variability is high, I would recommend you increase your sample size to even out or to compensate for that high variability in the numerator so that you can still keep your sample error or the outcome of your fraction kind of low. The fifth axiom is that you can take any finding in your survey. So let's say I do a survey among you guys in Marketing 470 and I ask about your age and your opinions and all sorts of other variables. So any of those findings, anything I find in the survey among my sample, I can replicate that survey with the probability sample of the same size over and over again. So I can send that same survey with those same questions I ask you to another group of similar students, another group and another group and another group. And I would be very likely to find the same results within a certain plus or minus range, so a certain margin of error of the original sample's findings. This whole idea, and I know that's a lot, I'm going to explain it more in depth with different words so that everyone fully gets it, but this idea is based on the central limit theorem. And the central limit theorem is a theoretical notion that allows us to assume a normal or bell-shaped curve, normal distribution, of the results of repeated surveys or repeated measurements. So a confidence interval is essential here. That's important to understand. So let me explain that concept first. A confidence interval is a range, so an interval, that has endpoints on the left and on the right side, so on the lower and on the upper side. And these endpoints of the range define a certain percent of the responses to a question. So you could say, for example, 95% of responses to a question will fall within this range, or 95% of all ages will fall within this range. So that doesn't mean everyone falls within that range, but the majority or a certain percent will fall within that range. And we usually adopt 95%. So really, in essence, what the central limit theorem allows you to say is that if you repeat a study X amount of times, so in, let's say, 1,000 times or 825 times or 5,769 times, you repeat a study a certain amount of times, then the results on a certain variable can be assumed to be normally distributed. If, of course, you do that with a similar sample. Of course, if you switch out your sample completely, if you take a very different sample in terms of demographics, then you will not have that same replicability of your results. But let's say you gather a random sample of college students, and then another random sample of college students, and another random sample of college students, and so on. Then you will find that whichever variable you asked in all of those surveys will be very similarly distributed, will be normally distributed. So let's take the example of legalizing marijuana again. And let's say I ask a group of people, let's say I do a referendum in the general US population, so a sample representative of the US population, and I ask them, would you vote yes or no, so in favor or against legalizing marijuana? And in this case, what I want to focus on is the yes voters, the people who are in favor of legalizing marijuana federally. So let's say in my sample, I gather a sample of US citizens. I find that 51% in that sample says, yes, I want to vote yes on legalizing marijuana. Cool, tiny majority. Now let's say I were to do another sample. So not the same people, it's not a panel. You gather different people, but the same size, same sample size, and same demographics. So again, a random sample. And I ask them again, would you be in favor of legalizing marijuana? And then let's say 57% says, yes, I want to legalize marijuana. And I do this again. And I ask them, would you legalize marijuana? 46% says yes. And we keep doing this again and again and again. Sometimes you have a little more percent of yes voters. Sometimes you have a lower percent of yes voters. So overall, with repeated studies, the percentage of yes voters for legalizing marijuana will follow a bell curve, as you can see right here. Then we can say that 95% of our repeated measures, so on the previous slide right here, 95% of all times that we asked people, or we took a sample of people and asked them, would you be in favor of legalizing marijuana? 95% of the time, so 95% of those replications will fall within a certain range. And this is called a 95% confidence level. And again, 95% confidence is a convention that researchers use in terms of what is acceptable for us in terms of confidence, right? And it corresponds to that 1.96 times the standard error, which is that constant that was placed in front of the equation there in the formula. So what does it really mean, 95% confidence? It means that we can say that if we did our study 100 times or however many times over again, we can determine a range or an interval within which the sample statistic will fall 95 times out of 100, so 95% of the time. This gives us 95% confidence that the real population's value will fall within that range. And of course, the real population's value is something you don't know. It's a parameter that you don't know. because you never ask the whole population because you're sampling. So all you have is your sample value or your sample statistic. To say it differently in different words, same thing, 95% of the samples drawn from a population will fall within the range defined by plus or minus 1.96 times the sample error. So based on this, we can say that we are 95% confident that the true population's value will fall within that range. So it's unlikely that the true population's value, so the estimate we're trying to get by sampling, falls outside of that confidence interval. So this is a way to really look at it, especially with the example of legalizing marijuana. If we find a certain range between which the amount of yes voters for legalizing marijuana would fall, we can literally visualize it on a graph and even calculate it. So let's say the percentage we find in our sample, and this in this formula we will just sketch it with an example. Let's say the percentage of yes voters in favor of legalizing marijuana in our sample is 50%. Okay, so we do a study and we find 50% of people is in favor of legalizing marijuana, then we automatically know that Q is also 50 because 100 minus P is Q. So Q is the leftover. Q is 100 minus P. And let's say our sample size also happens to be 100. So our sample size is 100 people. So we do a research study among 100 people. And in that group of people, we find 50% wants to legalize marijuana. Awesome. If we just drop those numbers in the formula and we were to calculate the formula, which I'm not going to ask you on the exam. You don't have to bring a calculator on the exam. But to help you understand it, I'm doing it here on the slide. So 50 times 50, in the numerator of the fraction, you have P times Q. So 50 times 50, which is 2,500, divided by N, divided by the sample size, which is 100. So you just plop that in there, and then you calculate it. Of course, 1.96 is that constant that we had. In this case, we come to a sample error percent of plus or minus 9.8. What that looks like is you can create a confidence interval with on the left side P minus 1.96 times the sample error, or P minus 9.8, which is 40.2% on the left side. And on the right side, we do P plus 1.96 times the sample error. So 50%, which was P, plus 9.8. Where did we get to 9.8? That was, of course, right here from the formula, which is 59.8%. So what we have is a confidence interval, a range between 40.2 and 59.8. So roughly speaking, the true population's percent of yes voters in favor of legalizing marijuana would fall somewhere between 40% or 40.2% yes voters and 59.8% yes voters. This is how estimates are made about any population's value. So you use your sample value to get an approximation or an estimate of the range between which, so the lower and upper limits between which your true population's value will most likely fall. And most likely, I mean 95% sure. So then this immediately also allows you to understand that if you increase your sample size, your sample error will go down. As you can see here, this is what we calculated. The Bordeaux red kind of color was with sample size of 100 people. And in that case, we calculated the sample error to be 9.8. Remember, just on a previous slide. Now, if our sample size was 500 instead of 100, our sample error would actually go down. If our sample size was even larger, if it was 1,000 people, our sample error would continue to go down, so it would be even lower. So that means our accuracy would be even higher because our sample error is even lower. Now, at some point, it's, like I said, not worth it anymore because of that law of diminishing returns. So you can keep increasing your sample size. It's never going to bring your sample error percent to 0. But what you can see in the graph is that as your sample size goes up from the red color to the light blue being a high sample size, a large sample size, you see that the graph becomes much more narrow, much more concentrated. That's because your confidence interval becomes much more accurate. You have a much smaller range. You see your range with the blue graph with the larger sample size is only somewhere between, well, and this is in the way so I can hardly tell actually, but let's say somewhere between 46, 47 and 53, 54, right? So that's a much more narrow confidence interval than for the red color, where the confidence interval is much wider, much more spread out, so you have a much less accurate estimation. The sixth axiom is that in almost all cases, and I do say almost because there's one exception, in almost all cases, the sample error of a probability sample is independent of the size of the population. So you probably noticed, or you may not have noticed, but in this previous formula that we covered, only small n, so non-capitalized n, was shown. That's because that was the size of the sample. Now, capital N, which is the size of the population, is nowhere to be found. We don't even talk about it. That's because the size of the population doesn't matter. It doesn't influence your sample error. In other words, even if your population is huge and you take a very small sample of the population, it's actually the sample size that influences your sample error and not the population size. The only exception is with very small populations, but that's not part of this class. We're not going to cover that. That's just an exception that I want you to know about for the sake of, accuracy of what I'm telling you. But the size of the population in most cases does not matter. In other words, a probability sample can actually be a very tiny proportion of the population. So you can gather a very small sample of a very large population and still have very accurate results, right? So a sample of 500 people from 1.3 billion people gives you a sample error percent of 4.4, whereas a sample of 500 people coming from, let's say, 375,000 people also only has 4.4% sample error. So same sample error. That's because it's the sample size that matters and not the population size. This table right here shows you again what level of sample error corresponds to a certain sample size. If you have a sample size of 500 people, you have 4.4% sample error. The last axiom is that you can make a trade-off between desired accuracy and the cost of data collection to calculate your ideal sample size. So the size of a probability sample really comes down to that trade-off you make between how much accuracy do you want, because obviously you want as high accuracy as possible, but you also know that a high accuracy comes with a cost because that means you have to collect more data. And we're going to cover that in the last session.